Okay, welcome to 9.2. 9.2 is an excellent review of chapters 7 and 8. We're going to go through all of that again. There's some new stuff at the beginning, and we're going to see how to put that into our calculator. So I have some calculator videos on the way too. Just a reminder that chapter 9 started with a discussion of being able to differentiate between matched and independent samples. So if you need to, go back and take a look at that again. We're going to be talking about matched, paired, or dependent samples. So that's our topic for 9.2. Now there are some shortcuts here. Now first off, if the lists are of different lengths, if you've got a different number of one thing and another, they are in no way matched. They have to be independent. Now, if they are the same length, if you have as many of each sample, you then have to ask the question, can you match? Or is there an element that goes with each of the first list with each of the second? So two things have to happen. There has to be exactly the same length. If there isn't, you know they're independent right away. And if they are the same length, you have to be sure that they're matched in some way. We're going to see an example where we're talking about a single patient at two different times as they recover from a heart attack. Now, if you are talking about matched pairs, so that's where we are right now. We're talking about matched pairs. And if you are talking about matched pairs, then there is a shortcut, and that's basically taking you back to chapters 7 and 8. We form the differences, and our calculator will do this for us, and then we do the single sample statistics, whether it's a hypothesis test or a confidence interval, for that list of differences. And this is easy to do on our calculator. So on a TI, we simply enter the data that we're interested in into the two lists, and then we form a third list that's nothing more than their difference. And then we go back to the methods of chapters 7 and 8. And those differences, D, are formed by taking x sub 1 and subtracting x sub 2, just like we did in the calculator with list sub 1 and list sub 2. We formed list sub 3 by forming their difference. So a lot of things that were x's in the example that we saw in chapter 7 are now d's. So take a look at what that means for the sample mean of the differences. So that second example, notice, instead of x bar, we now have d bar. It's formed by the sum of the d's divided by n. So we're now looking, basically, that d is telling us that we're looking at that list of differences. And then, of course, we have the standard deviation of the differences, so s sub d. And the standard deviation of the differences is exactly what you'd expect, except the x's have become d's. Now, the test statistic is of the same ilk. The only difference here is that x's have become d's. One of the other things that I want to point out, and we'll see this in just a few seconds, is that in this formula we need to know what mu sub d is. That is the mean of the differences. But this is a hypothesis test, and hypothesis tests often tell us some information. We're allowed to assume the null hypothesis. And so notice that in most cases, the null hypothesis is that there's no difference between the two populations. That is, that the mean of the differences is 0. So that makes this formula just a tad nicer. Of course, the p-value will come to us using a calculator. We'll use the t-test to do that. So here is a example. So we're looking at the cholesterol level of patients who had heart attacks. We measured those 2 days after the heart attack and then again 4 days after the heart attack. The researchers wanted to see if the cholesterol level of patients who have heart attacks reduces as the time since their heart attack increases. In other words, does the amount of cholesterol go down from 2 days after a heart attack to 4 days after a heart attack? Do the data show that the mean cholesterol level of patients that have had a heart attack reduces as the time increases? So that's our alternative hypothesis. We're going to say we're testing to see if that is indeed the case. Now, and it says to test at the 1% level of significance. So here's our data. So you can pause the video. This is exactly the same as in our workbook. Notice there's 28 patients here, and that the data is paired. So going into our calculator, we go into the stat menu, we edit that data. Notice that I have in L1 entered the data for the cholesterol levels 2 days after a heart attack, and notice that there are 28 of those. And notice that they're paired up with the cholesterol levels in L2. So we go over to L3, and then it's important that you go up. So make sure that L3, or that next list, is highlighted, and then enter the expression to form the difference, L1 minus L2. So list 1 minus list 2, and then press enter, and it'll form those differences for you. So here they are in L3. So notice that we see that patient number 1 has 2 pieces of data. We know that the cholesterol level after the second day for that patient was 270, and after the fourth day was 218. In other words, we can match up data from the first list with data from the second list. And we do that in the calculator by entering them in the same order. But that patient information tells us that the information that we're actually being given is in fact matched. Okay, so now it's our test to find the hypothesis test, to go through and do this. So the first thing we do is we state the random variable in words, and to do that we remind ourselves that there are 2. So x sub 1 is the cholesterol level of a single patient 2 days after a heart attack, and then x sub 2 is the cholesterol level of a patient 4 days after a heart attack. So what that means is that we can find D, and D is the difference, that is x sub 1 minus x sub 2. The parameters are the population means, so mu sub 1 is the mean cholesterol level of all patients 2 days after a heart attack, and no great surprise, mu sub 2 is the mean cholesterol level of all patients 4 days after a heart attack. And this is perhaps more important. Mu sub D is the difference of those population means, mu sub 1 minus mu sub 2. Now that's important because in a hypothesis test we do get some information from the null hypothesis. Remember, we're allowed to assume the null hypothesis. So we're going to say that the null hypothesis is that there's nothing really going on, that the 2 population means are the same. Mu sub 1 equals mu sub 2. Now notice that this is you can call it an algebraic expression. We could subtract mu sub 2 from both sides. And if we do that, we get that the mu sub D, that is the mean of the differences, is equal to 0. If you subtract mu sub 2 from both sides, you get a 0 on the right side, and you get mu sub D on the left side. So we're allowed to assume that. Remember, we're assuming the null hypothesis. Now, the alternative hypothesis comes from what it is that we are trying to establish. And we are trying to establish that the amount of cholesterol in heart attack patients reduces. That is, that the population mean 4 days after a heart attack, that is mu sub 2, is less than the amount of cholesterol 2 days after a heart attack, that is mu sub 1. So stated in the same order, 1 to 2, that says that the cholesterol levels were higher 2 days after a heart attack than they were 4 days after a heart attack. So we've got that inequality. Now, that's great, but that's not going to help us at all when it comes to the calculator. Again, we're going to have to subtract mu sub 2 from both sides and get that difference. So our alternative hypothesis, when we subtract mu sub 2 from both sides, Remember, we're still using that definition of mu sub d, which is mu sub 1 minus mu sub 2. And the moment that we have that, subtract mu sub 2 from both sides, we have the direction of our inequality. So when we enter the alternative hypothesis into the calculator, we're going to say that mu sub d is greater than 0. This is also where we state the level of significance. In this case, alpha is 0.01. Now we have to go through and check our assumptions. And at this point you might be saying to yourself, well, we haven't seen this before. And so let's just state it literally. It does not say that either sample is random. So at this point, that's exactly what we have to do. Now, the second thing that we're interested in showing is that this is a normal distribution. And that's fine, but we only have a sample of 28 patients. So this is when we have to remember that some things, like intelligence and height and cholesterol levels, we're allowed to assume are normally distributed for the purpose of this class. So that means cholesterol levels are known to be normally distributed. We don't have to worry about the sample size or anything like that. And remember, the last part of this test is basically ensuring that we're doing the correct test. And that is, we're doing a t-test. Why are we doing a t-test? Because the population standard deviation is not known. So at this point, we're going to put this data into our calculator, and we're going to get the sample statistic and the test. Okay, so we're now in our calculator, and we're looking at doing a t-test with that data that we put in L3. So we're going over to tests, down to t-test, and then we're using the data, that is L3. Our assumed mu is 0. Remember that that's basically saying that there's no difference. The list comes to us from L3, and we're interested in a mu that is greater than the that 0, that mu sub 0, the assumed mean. So we go down to calculate, and we get our data. So there's a reminder of what we're testing. We're testing that mu is greater than 0. Of course, we're doing a t-test in the context of differences, so that's mu sub d is greater than 0. There's our t value. That's kind of taking the place of z. It's very similar to telling us about how many standard deviations we are from the mean. And 3 is fairly large, and you can convince yourself of that by looking at the p-value. That p-value is really close to 0. Notice that when we round this to 4 decimal places, we'll have 0.0017. There's our x bar. Of course, that's our d bar. That's the average difference. So it looks like it was about 23 greater before to after. And then S sub x is really our S sub d. That is the standard deviation of the differences. And there's our n of 28. Okay, so now we enter our sample statistics, our test statistics, and of course the p-value. So x bar from the calculator, we were looking at differences. So that's our d bar that's rounded to 4 decimal places. And our standard deviation of the differences also looked like S sub dx in the calculator, but we were looking at differences, so that's S sub d. And then, of course, our t-score, 3.2189, and our p-score rounded to 4 decimal places. So that tells us that, well, that's well less than alpha. 0.0017, that is our p-value, is definitely less than alpha. So we reject the null hypothesis. Now we're going to say this in words, and we say this by saying there is sufficient evidence to say that the cholesterol level of heart attack patients decreases from 2 days after a heart attack to 4 days after a heart attack. Now that's fine, and that's what we did in Chapter 7, is we tested a hypothesis. But it would be kind of nice to know approximately by how much did it decrease. We were simply testing this hypothesis against sigma, a level of significance. But we might want to do a confidence interval. So now we're going back to the concepts of chapter 8. We're looking at intervals. This is a t-interval. That is because we do not know the population standard deviation. Steps 1 and 3 are the same. So those become steps 1 and 2 in the establishing that we're doing the confidence interval. And our new step 3 is to find the sample statistic and the confidence interval. And then if you're looking at what comes next for the sample statistics, those are exactly what we saw earlier. So that literally is copied and pasted from the difference, the sample mean of the differences, and the standard deviation of the differences from when we were doing hypothesis testing. And again, pairs there, not individual data points, but pairs. So the confidence interval is an estimate of the difference. So if you're asking yourself what that is talking about, that is talking about the difference of the population means. So we're basically now looking at a number by how much it went up or by how much it went down. So we can say that it went down if we've got a positive number. If mu sub 1 is greater than mu sub 2. We can say that it went up if we've got a negative number. If mu sub 2 is bigger than mu sub 1. Okay, so let's look at an example of finding a confidence interval. So it says, use the data to estimate the true mean difference between cholesterol levels 2 days and 4 days after a heart attack at a 95% level of confidence. So to do this, we're going to go to the calculator. We've already got L1 entered, L2 entered, and in L3 we've got the differences. Okay, so in our calculator, we go over to the stats menu, and then we go over to tests, and in the tests menu, we go down to a t-interval. Now, this is going to ask us for some data. We've got our data in L3, so we're going down to that list. Second 3, we'll enter L3, not changing the frequencies, but we've got a 95% level of confidence, so 0.95, and then we calculate. And when we do that, we've got our confidence interval. So there's our confidence interval, and our x bar is, of course, d bar. That is the mean difference. And s sub x is the standard deviation, not of x, but of the differences of those x's, s sub d. And a reminder that we had 28 patients. So we take that data back from the calculator and enter it in to answer the question, the sample statistics. D bar is the mean difference, and the standard deviation of the difference is from the sample. S sub d is also given. And those are the same as before, so you've seen those numbers before. And then new off of our calculator is the confidence interval, 8.4428 to 38.129. Now those numbers are positive, which means that the amount of cholesterol did indeed go down. It went down between 8.4 and 38.1 milligrams per deciliter. So the statistical interpretation is that there's a 95% chance that 8.4428 is less than the true population mean difference is less than 38.129. Now, we say this in words, it takes on a whole new meaning because it really is telling us something about the amount that the cholesterol levels fell. Between 2 and 4 days after a heart attack, cholesterol levels fall between 8.4428 milligrams per deciliter and 38.129 milligrams per deciliter.